1988, I wrote a popular science book called A Brief History of Time, which sold over 10 million copies. I say that not to brag, but to underline the deep fascination we all have with our universe.
"20 years ago, people rushed to buy physicist Stephen Hawking's book. The public were drawn to Hawking because he's a mega brain trapped in a body that doesn't work. He said he would tell us how the universe worked and how it began. But Hawking is now almost completely paralyzed. These programs are a journey into the mind of Stephen Hawking and his lifelong quest for a theory of everything. Stephen Hawking is the most famous physicist alive. The world sees him as the celebrity egghead in a wheelchair.
Let's go.
But he doesn't see himself as a genius. He sees himself as one of those lucky people who get paid to do what they love. It's just that his job is a little bit different from most people's. 20 years ago, Hawking said he wanted to know the mind of God. He felt he was on the brink of delivering a simple, elegant set of laws that would explain everything in our universe, and more importantly, how it arose.
How can we understand the universe? Is it arbitrary, or is there a grand design? Do we still need a God? 20 years on, my need to find answers to the fundamental questions about our existence is undiminished.
In 1963, while studying for his PhD in physics, Hawking was told he had Lou Gehrig's disease. It turned out to be the slowly progressing form. As a student, Hawking had, by his own admission, become somewhat directionless. Faced with an uncertain future, he became fiercely determined to do what he could to advance the field of physics. Professor Bernard Carr was a graduate student of Hawking's and became his close colleague.
And of course, it's required a huge amount of effort for him. But it's, in some sense, I think, given Stephen the determination to overcome the problems, and it made him even more determined, I think, to sort of, to crack the ultimate problems of physics.
So Hawking set off to crack the ultimate problem of physics. For him, it was not enough just to explain how one little bit of the world over here worked, or answer simple questions like, what makes the Earth orbit the Sun? He was after a complete theory of everything. Despite his disease, Hawking was attempting to do what almost every other physicist thought was impossible: to unify the two great theories of physics, the theory of the very large, Einstein's theory of relativity, and the theory of the very small, quantum mechanics.
My life's work has been to unify the theories of the very large and the very small. Only then can we answer the more challenging questions. Why are we here? Where did we come from?
It's a quest that, despite near total paralysis, he's not about to give up on.
He's a very tenacious, courageous individual, but he never thinks of it like that. He just gets on with it. That's really how he gets on with everything. can be quite exhausting as well because, very demanding. He doesn't get tired like the rest of us. We all get very tired, but he can keep going.
Physicists love to explain how our universe arose and how it works. We understand enormous amounts. But when asked how did it all come to be, we don't have one single answer yet. Can I have a minute, please?
Stephen Hawking, the Lucasian Professor of Mathematics at Cambridge University, a post once held by Sir Isaac Newton. Age 66, Hawking still tirelessly puts in a full week of teaching and research. Hawking's schedule is frantic. As well as trying to find out how our universe came about, he tries to satisfy an incessant demand for his illustrated lectures.
Can you hear me? According to the Bashango people of Central Africa, in the beginning there was only darkness, water, and the great god Bumba. One day Bumba, in pain from a stomach ache, vomited up the sun. The sun dried up some of the water, leaving land. Still in pain, Bumba vomited up the moon, the stars, and then some animals. The leopard, the crocodile, the turtle, and, finally, man. This creation myth, like many others, tries to answer the questions we all ask. Why are we here? Where did we come from?
Why are we here? Was a question Hawking asked himself a lot back in 1965, while contemplating what the doctors had told him might well be a very short life ahead. Then he heard reports of a lecture given in London by a brilliant young mathematician, Roger Penrose.
Sorry to interrupt, but Roger Penrose is here. I was wondering, shall I bring him up?
Yes.
Thank you, Stephen.
Penrose's groundbreaking work catapulted Hawking out of his depression.
I certainly remember Stephen in lectures asking extremely awkward questions at the end of seminars or in the course of seminars. That was the thing that struck me particularly about him. Very penetrating questions, I should say, not just awkward.
Penrose had given Hawking a glimpse of how physics could be used to answer the question, why are we here? Penrose and Hawking were already experts in Einstein's theory of relativity, the theory of the very large. It's a theory about our universe and how it works. We live on a tiny planet, in a tiny galaxy. But Einstein's equations apply to the vast leagues of stuff in between, empty space. As physicist Pedro Ferreira explains.
Now, let's imagine that this enormous library is our visible universe. And we know that the universe is sprinkled with galaxies, and I really mean sprinkled. There's a lot of empty space around each galaxy. Let's take our galaxy, the Milky Way. It would comfortably fit in a full stop in Stephen's book.
Our galaxy is microscopic compared to the gigantic tracts of empty space that dominate the universe. But Einstein showed that all that empty space turns out to have some remarkable properties.
Let's imagine that this basketball is a celestial object like a star, okay? And let's imagine that this bookshelf with these books is space. In our classical view of space, it would be rigid like this. It would just be this static thing, this thing that is unresponsive. But in our modern view, this star, as it moves through space, it warps it, it dents it, it bends it. And other objects that then move through this space will feel this warp, will feel these bends, these warps, and will move according to that. They won't move in straight lines. They'll feel these bends and they'll curve.
The fact that big objects, like stars, can actually bend and curve space is now an everyday notion to astrophysicists like Kim Weaver.
What we're talking about in terms of astronomy and cosmology are objects that have a huge amount of mass. A planet-sized object, or a moon-sized object, or a star-sized object. The mass of this object bends space around it. If the ball here that is at the center of the sheet is representing the sun, and this penny is representing a planet like the Earth, then you can use the penny to demonstrate how the Earth orbits the sun.
We think the force of gravity makes the heavens turn. What physics says is actually going on is planets orbit stars because they're trapped in areas of curved space. The Earth is actually rolling round and down into a dimple in space-time caused by the sun. The penny rolls in quickly, but of course, it'll take the Earth billions of years to hit the sun. The Earth also causes space to bend around it. What we think we feel as the force of gravity is, in fact, the strong curvature of space around our planet. According to Einstein, when astronauts slip the earthly bonds of gravity, they're actually escaping the strong curvature of space. But Penrose and Hawking were about to do more than just bend space. They were going to turn it right back in on itself and conjure up black holes. Young Stephen Hawking was electrified by the work of Roger Penrose.
It just marks time outside. And I'm going to draw this.
Many physicists thought black holes were just a crazy idea, but Penrose had proved they must exist. It takes the death of a massive star to make a black hole. As a star burns down, all of the waste products are drawn into its center. The center of the star becomes so heavy that a teaspoonful would weigh more than a mountain range. All the while, around it, space is being curved back in towards the center. Finally, this curvature of space, the effect of gravity, becomes infinite. Not even light beams can escape. Around the ultra-dense center, there forms a sphere of darkness that we now call a black hole.
If we take something like the Sun, if that were to form a black hole, then the size would be about a few kilometers. If the planet Jupiter were to collapse into a black hole, it would have a size of a few meters. So this black sphere here will be a good representation of what the black hole formed by Jupiter would look like. If the planet Earth was to collapse to a black hole, it would be even smaller. It will be a few centimeters in size, so that might be a representation of the planet Earth.
But Penrose hadn't just shown that the Earth could be compressed to a black hole the size of a tennis ball. What excited Hawking was that Penrose had proved, using Einstein's equations, that at the center of a black hole there was a plug hole, down which matter, space, and time disappeared. The plug hole had a fancy mathematical name, a singularity. Hawking was excited and mystified.
In 1965, Roger Penrose showed that if a star collapsed below a certain critical radius, it would inevitably develop a singularity, at which time would come to an end. At first, I didn't understand either the significance or the proof of this result.
Hawking became obsessed with understanding the singularity. It was a strange choice of specialist subject. A young man who'd been told he had 2 years to live was wrestling with a point in space where the universe disappeared out of existence. And amazingly, Hawking turned the plug hole of death on its head.
Now, what Stephen showed, the first thing he did in this area, was to show that the same argument can be used in the reverse direction of time. This argument applied to time going that way.
Hawking had the brilliant insight to reverse Penrose's equations and apply them not just to a black hole, but to the entire universe. If bits of space could disappear down the plug hole of a singularity, perhaps everything in the universe had originally appeared out of one. In what was his PhD thesis, Hawking made a huge breakthrough. He proved that the universe had to have appeared out of an incredibly tiny single point. It was a fabulous result, but it was also the science equivalent of shooting yourself in the foot. He could prove the universe started from a tiny single point, but frustratingly, not how or why. It seemed to many that this inexplicable, sudden appearance of the universe, expanding out of a microscopically tiny point, had to be a miracle.
There are two attitudes one can take to the results of Penrose and myself. One is that God chose how the universe began, for reasons we could not understand. At a conference on cosmology in the Vatican, the Pope told the delegates that it was okay to study the universe after it began. But they should not inquire into the beginning itself, because that was the moment of creation and the work of God. I was glad he didn't realize I had presented a paper at the conference, suggesting how the universe began. I didn't fancy the thought of being handed over to the Inquisition, like Galileo.
Hawking's response to his results was to decide that the equations he'd used, Einstein's theory of relativity, were not the whole story.
General relativity makes a prediction that the universe was once infinitely small, but it loses the ability to describe the universe when it was tiny.
Hawking was pretty sure our entire universe did start out as a tiny dot, but he wasn't going to be happy until he could describe how that dot came about. Hawking had laid down a huge challenge for himself and the rest of physics.
The bottom line is, Einstein's equations are useless at the instant of the Big Bang. We physicists say that long time ago, the universe was so small, it was smaller than a basketball. You could put the universe in your pocket. It was smaller than an electron. Some people call it a singularity of infinite gravity. Now, that's silly. There's no such thing as infinite gravity. It just means that we use the word singularity to hide our ignorance. We don't know what the singularity is.
Unraveling this singularity, this tiny point of creation, became Hawking's life's work. But just showing that the whole universe arose from a single tiny point was not enough for Hawking. He wanted a complete theory of everything, a theory that would describe the moment of the universe's creation in precise detail. And again, black holes would point the way. In the early 1970s, black holes were the agents of death, the place where everything we know about the cosmos came to a chilling end. But to a young physics researcher like Stephen Hawking, they were an exciting challenge.
My own work on black holes began with a eureka moment while getting into bed in 1970.
What he'd glimpsed that night, getting into bed, was something very peculiar about black holes. It was something that started to deeply trouble Hawking. But it would turn out to be the key which unlocked the door to the mystery of creation. In the mid-1970s, Stephen Hawking was about to attempt something no other physicist had ever achieved. For 50 years, physicists had failed to meld and shape Einstein's theory of gravity. It would not fuse with the very different theory of how atoms work, quantum mechanics. But what Hawking had glimpsed was a point where the two must clash, at the very edge of a black hole.
What happens if you have a black hole which is sitting there? It's black. That's why it's called a black hole. No light comes out of it. What happens if you include the effects of quantum mechanics?
Einstein's theory said the black hole was a smooth, perfect sphere. Hawking plunged it into a sea of particles and atoms. The two theories sputtered and fought each other. Somehow, Hawking had to bring them together.
The problem of reconciling Einstein's theory with quantum mechanics is one of the holy grails of modern physics. What Hawking did in the early 70s was he didn't try to solve this problem completely, but he tried to put quantum mechanics and general relativity together in a very limited fashion.
What was all the more remarkable was now, unable to write down long equations and calculations, Hawking had to imagine the whole process in his head. As well as space and black holes, Hawking had to visualize a world we are all unfamiliar with, the bizarre realm of the atom.
A good way to think of an atom is a bit like our solar system. You've got a nucleus at the center, and you've got electrons whizzing around. Now, let's imagine that this marble is the nucleus of an atom. An electron will be the width of this hair. Now, again, we're used to seeing in textbooks that an electron is more or less this distance from a marble. But it's not. It's not this far. It's not this far. It's not this far. It's not even this far. Not even here. On this scale, where the nucleus is the size of a marble and an electron is the width of a hair, the electron would actually be 2 miles away from the nucleus.
At the atomic level, particles are almost not there. They're less like solid lumps of matter and more like tiny, empty force fields. And as force fields, they shimmer. They're more like waves. Water, sound, and light can behave like waves, but so too can the parts of the atom. And that means they can spread out to be in more than just one place at a time.
Common sense says that when I fire this gun, one ball hits one target. That's it. If this is an electron gun hitting many targets, I find out that one electron has a probability of hitting many targets at the same time. Now, that violates common sense. I thought it was one ball, one target. In the quantum world, common sense is violated. Common sense has no place in the quantum world.
Hawking knew that atoms were not like little billiard balls. They turn out to be much more erratic. How could he join Einstein's stars and planets that float sedately along nice curved lines with atoms that buzz around in a frenzy?
At a very tiny level, our universe is like a crazy dance of waves, jangling to a myriad of beats. Particles appear and disappear at random. And at this level, nothing is certain, not even existence.
Atoms are a bit like people. They're very hard to predict with absolute certainty. They do roughly what you would expect of them, but never exactly. With atoms, it's hard to be totally certain whether they exist or not. Sometimes, Hawking knew atoms pop up where there should be absolutely nothing around. In fact, out in space, it happens all the time. Space, the void itself, cannot have exactly zero energy. At an atomic level, there's always a tiny, tiny amount of activity going on. So Hawking asked, what happens when the perfectly smooth sphere of a black hole meets this microscopic energy field of space? In empty space, this energy takes the form of pairs of subatomic particles that emerge out of the void, exist for less than a nanosecond, and then annihilate each other.
So the idea is that out of nothing, if you like, a pair of particles is created and then exists for a short time and then annihilates. And that's happening throughout space. So it's happening there, and it's happening there, and it's happening there.
This pair of particles is like yin and yang, opposites that would not exist without each other. One has positive mass, and the other, strangely, has negative mass. But Hawking asked, what would happen if that negative mass particle bumped up against a black hole? Hawking realized that the positive particle would have just enough energy to escape the black hole. But the particle with the negative mass would fall in, and it would do something extraordinary to the black hole.
The particle that goes inside the black hole eventually decreases the mass of the black hole. It effectively has negative mass, but the particle that goes off to the distant observer is there observed as part of radiation.
Although we now understand why black holes have to give off thermal radiation, it came as a complete surprise at the time. At first, I thought I must have made a mistake.
But Hawking had not made a mistake. Around a black hole is an almost imperceptible microscopic glow. Positive mass particles fly off from it, behaving just like thermal radiation. Negative mass particles fall in. Slowly, almost imperceptibly, they decrease the mass of the black hole, and this eventually has catastrophic consequences.
So, what the Hawking result implies, it means that the black hole, instead of being black, is actually always emitting radiation. And so what is happening is that for most of its life, the black hole is gently sizzling away, but eventually it gets smaller and smaller, the temperature gets hotter and hotter, and eventually it gets to a point where it's so hot that it essentially explodes. It loses all the rest of its mass in a very, very short time.
The black hole had become a sizzling bomb, just waiting to go off.
When black holes were first thought of, and when I first started studying black holes, even I remember thinking, oh, a black hole, it's the end of everything. A star collapses down and everything disappears into it, and nothing ever comes out, so maybe it's really boring. But really, black holes represent our best way to have an ultimate test of the physics of understanding the universe.
And astronomy has borne out Hawking's discovery. In fact, it seems that every galaxy in the universe may have a supermassive black hole at its very center.
Black holes are not ultimate endpoints. They really are beginnings of something, because around a black hole, you have enormous amounts of activity going on. You have stars being ripped apart, and you have disks of accreting matter swirling around. You have cauldrons of heat and light around a black hole. You have jets being produced by a black hole. You have particles coming out at half the speed of light, being shot away from a black hole. You have stars being born around a black hole. There's an enormous amount of stuff going on, caused by the fact that that black hole is really there. And that's exciting.
Hawking had taken a great leap forward in his quest. He'd linked the theories of the big and the small for the first time ever in physics.
What was really amazing about this paper, really one of the most beautiful papers in the 20th century, is that his argument that this could happen relies on almost no assumptions. The assumptions about the nature of quantum mechanics and the nature of general relativity that basically every living physicist will agree with.
But Hawking had done more than just show that a black hole was a little bit fuzzy. The theory of the very tiny was starting to unlock the secrets of the very large. Could he now unlock the secrets of the moment of creation?
By applying quantum mechanics to the edge of the black holes in the 1970s, I was able to revolutionize our understanding of them. To expand our understanding further, we need to bring quantum mechanics into the heart of the black hole.
Could Hawking use the theory of the tiny to explain the birth of our entire universe? This world that is so familiar, how did it come about? Can we ever discover how all this came to be? Stephen Hawking runs a department that is urgently trying to find the answer.
He has his PhD students and they have supervision and they come in every week and they have lunch and they talk about ideas, and if they get stuck they can come to him. You have to have exceptionally good students to be able to cope with the heavy work that they have to have, and also with the communication. They really have to know their subject.
How have you all survived the summer?
Very well.
Start.
Go.
Age 66, when many are retiring, Hawking shows no sign of giving up the quest.
The food's improved since I was a student. Has it improved the work rate of the students?
No.
I think he's quick there. I think he's in best proportion.
Hawking's life's work has been to come up with a theory of everything, a theory that explains how our universe works and how it arose. In the 1970s, he had huge success using the theory of the tiny, quantum mechanics, to better explain black holes. But in the 30 years since, using it to explain the entire universe has turned out to be just a bit harder.
Nevertheless, even though the job has been more difficult than one might have hoped, I think there is still every indication that there is a final theory and that we may get there, but it just proves much more complicated than we originally hoped.
Not surprising, really, that it's been hard. Hawking's trying to peer back to 13.7 billion years ago, to the start of everything. His main stumbling block has been getting the theory to explain what the entire universe was like back then, when it was all compressed to a size smaller than an atom.
Although the universe is very big now, the observable universe is something like 13,000 million light years, the distance light has traveled since the Big Bang. We know that that entire region must once have been compressed into a very, very, very small scale. But of course, once the universe is compressed into a very, very small scale or a very, very high density, we know we are in the domain of quantum theory.
But even though the universe was once tiny, the amount of energy and gravity that it contained was vast. Getting the theory of the tiny to explain that huge level of gravity has proved impossible so far.
If we want to know what happened when the universe began, we have to have a theory that can describe gravity on a very small scale.
For the last 30 years, Hawking has struggled to find a way to describe immense gravity with quantum theory. But he has faith that the theory of the tiny will eventually win through. And there's evidence that supports his belief. Just as atoms are fuzzy and erratic, it seems the universe was too when it was tiny. And the evidence comes from satellite observations of the heavens. Since the late 1960s, scientists have known that there is leftover heat radiation from the Big Bang. It's a tiny amount, but recent satellite missions have shown that this leftover heat is not smoothly or evenly distributed throughout the universe. WMAP is the latest satellite to refine our picture of this echo of the Big Bang. Dave Spergel is part of the WMAP team.
What WMAP's seeing is variation in temperature of a few millionths of a degree. That results in more matter being here than over there.
WMAP supports Hawking's reasoning. This is the image of our universe today, which WMAP has produced. The colors indicate tiny differences in temperature. If Hawking is right, the differences started right when the universe was the size of an atom. This picture is like a massive projection of what was going on at the beginning of everything. The universe was uneven or fuzzy at the start, and that unevenness has evolved into the different parts of the universe we see today.
That may not sound that important to you, but because there's more matter here, a galaxy is going to form here, and we're going to live here, and there'll be nearly empty space here. By studying the properties of these fluctuations, we can learn about the quantum mechanical fluctuations in the very early universe that gave rise to what we see, and us.
Without tiny quantum fuzziness affecting the Big Bang, huge galaxies would never have formed. A perfectly spherical explosion of time and space would not have done the job. It is the roughness of the moment of creation that gave rise to matter and galaxies. As Hawking suspected, we live because of the imperfections of creation. Hawking is forging ahead on his quest for a theory of everything. Today, all of physics is racing alongside him. Incredible experiments are now being built in outer space and deep underground, which will try and probe deeper into the very moment of creation. There is excitement in the air, a sense that the answer is just waiting to be found. Whether he finds it first or not, Hawking is philosophical about his part in this great journey.
I was unlucky to get motor neuron disease, but lucky in almost everything else. I have 3 very attractive children, success in my scientific work, and a real sense of satisfaction at having achieved all this, despite the difficulties. Not many people can say this.
Is there anything you wish you'd achieved professionally, perhaps, that you haven't already?
I feel I have achieved quite a lot, but one would always like to have done more. In particular, I would like to have found a complete theory of quantum gravity in the early universe. Still, that wouldn't have left much for anyone else to do.